Okay, welcome to the 8th class meeting of EC 202, Introduction to Probability and Random Processes. So let's start by reviewing not everything, but important things learned in the last class meeting. I have chosen the starting point as the Gaussian random variable. And in more cases, people call it normal distribution. And the PDF is very, very famous and well known. And most of the courses, probability courses, statistics courses, and my course also ask you to memorize this PDF because it's so important. And also, it gives you some hints when you scale PDF, shift PDF, something like that. So last time, I asked you, what is the integral of this function, e to the negative x squared? And one-dimensional integration never gives you the answer, but you may square it and convert the Cartesian coordinate to polar coordinate, including Jacobian. And then you can find that the integral is square root pi, something like that. And then you normalize properly and have this form. This is the integral. This integral gives you 1, whatever sigma and whatever mu you have. So a Gaussian family, we are going to see, Gaussian family of PDFs or Gaussian family of CDFs, or if you just want Gaussian family of distributions, are parameterized by only 2 real values. One is any real value possible. This is non-negative real value. The reason why I say non-negative is that there are some cases called degenerate Gaussian. In that case, parameter sigma square equals 0, and the PDF is not this bell-shaped curve, but a direct delta function. However, probably some of you remembers from your textbook, I'm not sure which textbook you use in signals and systems, but when you define a direct delta function, not just this rectangular pulse is used. Sometimes we use Gaussian pulse. And we shrink this width. And then the height explodes. And actually, this Gaussian time function, in that case, well serves as the direct delta function if sigma is small enough. Of course, other functions, even sinc function you learned in signals and systems, sinc function can serve as the kind of approximation of the delta function. So to talk about direct delta function, never think in this way. It's a limit of a rectangular pulse. No, that is not true. That is a very simple way to understand what is a direct delta function, but that's totally wrong. So any pulse with finite integral shrinked in the time domain can serve as a direct delta function. The good thing for other functions is that they are differentiable. So if you just consider derivative of rectangular pulse, then again you have delta function and you have the headache. But if you have a Gaussian pulse or a sinc pulse, it's infinitely differentiable. So you can easily understand why, for example, this differentiation of delta function is sometimes written that way, okay? Anyway, so I ask you to memorize the PDF of the Gaussian. And I prefer writing this way. You see, I have taken sigma square out of the square root, and I have grouped x minus mu divided by sigma in the exponent. Why? Because if you shift the value of mu, then nothing changes in the coefficient. However, if you change sigma, that also appears in front of the density function. So if you increase sigma, what happens? It kind of extends. And we know that the density must integrate to 1, so height must be scaled down. That appears here. So please remember this one. By the way, this x minus mu divided by sigma is so important, and that is used for standardization. And as I mentioned already, the Gaussian family can be represented by a single president. What is that? Standard normal. Zero mean unit variance Gaussian can represent all the Gaussian density functions. How? Through this standardization. So here, capital F is the CDF of the standard normal distribution. And this capital F sub x is normal with mean mu and variance sigma square. Got it? So any Gaussian CDF can be rewritten in terms of the standard Gaussian CDF. Sometimes this function f is called phi function. So where it is? Yeah, this is red phi function. And the complementary CDF of standard Gaussian is often called Q function. So phi, you can write it phi of x plus Q of x becomes 1 because it's the summation of CDF and the complementary CDF. By definition, they must be 1 for all x. By the way, the CDF of standard Gaussian, not only standard Gaussian, all Gaussian, except that degenerate case, has very, very messy integration. It's, let me show you again. So this is CDF, and you have improper integral with infinite integration interval. So it's not easy to even numerically tabulate this result. But since no closed form exists, people usually tabulate. And some engineering subjects love not the Gaussian CDF, but so-called error function. So they have a little bit differently scaled version of the bell curve, and they have tabulated error function. One good thing is that, for example, popular programming tool MATLAB not only has Q function built in, but also error function, and also complementary error function and complementary phi function, which means Q function. So that's good. However, remember this one. The Gaussian CDF does not have closed form. What does that mean? We need tabulation, 테이블화가 필요하다. 이렇게 이해하시면 됩니다. So that is one way, but sometimes we need still not the table, but some formula, mathematical formula. In that case, this is a very, very good approximation, and it will appear again later. And there are some approximations, but forget about this one. And some of you may observe that one in your graduate course. But most interesting twist of the Gaussian CDF is this one, CCDF. So Q function now has turned to be a proper integral with finite integration interval. And again, you cannot just convert the one-dimensional Q function definition using any change of variable. You can never reach this one. Again, the hint is that you consider in 2 dimensions. And also the hint is that there is theta usually used to represent an angle, and we have 0 to pi over 2. That is the hint. So if you really love to investigate on this Craig's formula, then it could be a very, very good topic for your voluntary project. You may choose to submit at the end of the semester. Anyway, I'll be back about the log-log plot and power law when I talk about Cauchy distribution today. Anyway, so we've seen a Gaussian family, and there is more than one important family of distribution functions. There are many, and what is important is that these density functions have only a few parameters just put together to be written as theta underline. So it's a vector of length, some 1, 2, 3, something like that. In Gaussian case, as I told you, you may regard this one consisting of mu and sigma squared. Sometimes single parameter is enough for a family. Sometimes several parameters are required. But anyway, you must pay attention to the use of semicolon because we don't know in many cases whether these parameters are to be modeled as random variables or not. So if you study machine learning, sometimes these parameters are regarded as random quantity, but sometimes are not. You must distinguish these two different cases. Got it? Usually, very careful writers of textbook or professors teaching courses, they intentionally use semicolon in order to emphasize that these parameters may not be random quantity. It's just unknown deterministic variables. Got it? Anyway, sometimes you use probability mass functions to parameterize the distribution, sometimes PDF, sometimes CDF. So you have freedom. Why do we use this parameterized family? Because in general, distribution, CDF, PDF, whatever, is so complicated. Just consider PDF. Any shape, non-zero that integrates, non-negative and integrates to 1, then any function can serve well as a PDF. Then how can you assign just a few parameters for that density function to describe it? You need uncountably infinite pair of xn density at that x, right? So parameterizing itself is a huge, bold move. Just you use only a few parameters. Why do we do that? That is important. You must remember the reason why we love parameterized family. There are usually two reasons. One is that what we observe really follows that simple parameterization. In circuits, for example, as we will see, the thermal jitters of electrons really gives us Gaussian distribution. However, sometimes our distribution is far from Gaussian, but we just try to use it. And you may say that, well, there should be very large error. Interestingly, under certain conditions, it's okay. Sometimes your assumption of Gaussianity of what you observe does not give you much penalty. It turns out that you just derived linear system, linear optimal system. So sometimes Gaussian assumption looks very absurd, but still gives you some kind of optimality in your statistical inference. So probabilistic modeling with only a few parameters are not always an absurd thing. In many cases, it's a very clever move. Got it? By the way, at the end of the last class meeting, I emphasized this one. What was that? Our elementary school joke, right? You have one cup of water plus another cup of water becomes one big cup of water. What is wrong? When I was an elementary school student, I also claimed that, hey, size of these cups are different. But what is important is that you have units in the real world for every real number. Every physical quantity has units. And if you assign units to your variable of your outcome from random experiment, then your, for example, probability density function suddenly have units. So let's see that. First, we consider discrete random variables, family of discrete random variables. This is still review. We've seen Bernoulli and binomial and discrete uniform and what else? Exponential. That was quite interesting, right? We had memory list property, discrete memory list property for discrete exponential. And we also had 홍씨 부모님의 분노 related hypergeometric distribution. And you've seen this problem already, but usually you use one of the two approaches to show that the parent was wrong. And at the end of last class meeting, I talked about Poisson distribution. Poisson distribution, as it is classified as a discrete random variable, is about number of counts. So it's like this. Suppose you are serving in Burger King. And here is, even though now kiosk replaces that, but anyway, here comes your customer. And you count the number of customers arriving to your counter during last 5 minutes. An interesting thing is that if we model the inter-arrival time between these customers as independent, then suddenly your number of customers during last 5 minutes follows Poisson distribution. So Poisson distribution and continuous memory list random variable are very, very closely, tightly related. Anyway, and this distribution looks like this, the probability mass function. And as you see here, you have negative lambda in the exponent of the exponential function. Since exponential function is a transcendental function, which is defined as a Taylor series, its argument should not have any unit. So here, lambda is a unitless quantity. However, in many cases, you observe something like this. So X follows Poisson distribution with parameter lambda t. But here, we have notation like X follows Poisson lambda. What's the difference? In this case of lambda, it's unitless and appears here. In this case of lambda t, the product appears instead of lambda here. So if this lambda, different from the above one, has some per second unit, then this t has second unit. So their product becomes 1. And you will see anyway. Today, we start with families of continuous random variables. Most of the distributions are well known and you already know. You learned in probably highly likely in probability and statistics. The first one is the continuous uniform. The reason why we have this modifier of quantifier is that we also have discrete uniform distribution, and we've seen. And here goes the notation. And it looks like this. This is the PDF, and this is the CDF. CDF is monotone increasing. And since we have no point message at plus minus infinity, we have this convergence to 0 and 1. And this is related to the kind of deterministic burst type problem. So suppose you want to write a bus that exactly have 10 minutes difference between consecutive buses. Now you arrive the bus station randomly. Then what is the distribution, probability distribution of your waiting time? And you can easily show that your distribution is exactly discrete uniform. So here goes your PDF, and if the unit of this x is minute, t is minute, then this is 10, 0, 1 over 10. Got it? And let me ask you another question, even though that is to be taught in today's course. Suppose you arrive at the bus station and you have waited 5 minutes already. Then conditioned on that event, what is the probability distribution of your waiting time from now on? And it's not difficult to see that has distribution like this. Sorry about that. Should be differently. Just a second. Oops. Yeah, probably like this, right? So in this case, t is greater than 5. So you have waited 5 minutes. What is the waiting time from not right now? So this is your waiting time. And this is kind of follows the common sense. You already have waited 5 minutes. What is the total waiting time? That is the distribution. So it's okay. Now consider exponential distribution having distribution like this. Of course, usually we have this offset A equals 0. And in that case, we have this type of distribution. And you may wonder why suddenly I use capital T instead of X, because exponential distribution is the counterpart of discrete geometric distribution. This distribution. And when I mention the property or character of geometric distribution is, what was that? It's a discrete memoryless distribution. And actually, exponential distribution is the continuous counterpart. It's related to continuous memoryless property. What is that? Suppose T, capital T, is related to your waiting time. And you compute this probability. So suppose you already waited t0 minute. And given that, what is your waiting time? Amazingly, your so far waited time does not affect. This is memoryless property. And this memoryless property is very, very important and gives us something counterintuitive. Suppose now that you have buses allocated this inter-arrival time as exponential distribution. Then you arbitrarily go to the bus station. And suppose the mean of this exponential distribution is 5 minutes. In the previous continuous uniform example, since the buses are exactly spaced 10 minutes, your average expected waiting time was 5 minutes. So here again, you have 5 minutes expected waiting time. So far, it looks no problem. However, as I told you, if the buses, the difference is not deterministic, but follows exponential distribution with mean 5 minutes, then you suddenly have this memoryless property. You are waiting 3 minutes, even 9 minutes, even 10, 11, 20 minutes does not affect your expected waiting time. Still, your expected waiting time is 5 minutes. And you may say that this is absurd. Yes, you are right. But sometimes this type of memoryless property makes everything very, very simple. For example, some of you are taking Introduction to Communications and Networks, and you are studying the Internet protocol. You are going to study Internet protocol. And sometimes we find something strange in the basic design of the TCP/IP. If you were the initial designer, probably you wanted to favor some packet that is lost several times. You want to somehow increase the packet successfully delivered to the end a little bit higher. But they didn't choose that. Actually, they intentionally didn't favor lost packets, retransmitted. And that actually makes the distribution, some inter-arrival or some related time difference as very, very exponential. Then, as you will see later in this course, this number of packets arriving in a router looks like Poisson random process. And inter-arrival distribution looks like IID exponential. In that case, we can easily split the arriving process. We can easily add different arriving processes to still have a Poisson distribution and to still have exponentially distributed inter-arrival time. That makes analysis very, very simple. So I personally believe that the original designers of the internet intentionally didn't give any priority to the repeatedly transmitted but lost packets, something like that. Anyway, the next one is Laplace distribution. And as you see, it looks very similar to Gaussian in the sense that we have something like this, right? And as I told you, whenever you have B dividing X, you have 1 over B in front of the density function. Why? Because the density must integrate it to the unity. Right? Anyway, if you increase B, what will happen? In Gaussian, B corresponded to the standard deviation. So if you increase B, what will happen to this Laplace distribution? Again, it extends its distribution. Right? Same thing happens. The difference is that its PDF is very, very pointy here. It's not differentiable here. Okay? But if you increase B, then as you see, it decreases the height and it extends more to plus minus infinity. By the way, this Laplace distribution is often used to mathematically model quantization noise in your digital signal processor. So you will see later in other courses. Here comes the most important, actually second most important, because Gaussian is the most important continuous random variable. This Cauchy distribution is the second most important distribution. And let's see its shape. First, as you see here, even though I really hate this parameterization, probably I loved this type of parameterization, but anyway, sometimes we put the parameters not in the subscript, but next to the argument of the function. Some old textbooks or even modern textbooks really hate putting subscripts of subscripts. But I love that. So I prefer this one because it's more clear. It says that it's a density function of X parameterized by X0 and gamma. But anyway, so as you see here, again, we have X minus X0 divided by gamma. So you now has become the Pavlov's doodling dog, and you find 1 over gamma here. Voila, right? We have 1 over gamma because we have divided X with gamma. Now, different from Gaussian that had exponential function, it has 1 plus X squared type thing in the denominator. But still, if you draw PDF, it looks quite like a bell curve. Last time I said that bell-shaped curve has 2 things. there are a bell-shaped curve and the bell-shaped curve. And this one, bell-shaped, really means it looks like European bell, right? But here, the bell curve or bell-shaped curve means Gaussian distribution or normal distribution, usually, okay? What's the difference? If you draw it in the linear scale, it's hard to distinguish Gaussian from Cauchy. It looks almost the same, right? And CDF looks very similar. Gaussian CDF also looks like this. But they have huge difference if you use log-log plot. And here goes the complementary CDF of Gaussian and Cauchy. Last time, I emphasized the so-called power law when you use log-log plot. Now, this has logarithmic scale and also horizontal axis has logarithmic scale. And you see something like straight line, and its legend says that that dashed line is for Cauchy CCDF. What does that mean? Cauchy distributions, complementary CDF, follows power law. However, Gaussian does not. It's decaying very, very fast, faster than any straight line. This is called a waterfall curve in log-log plot. And this type of curve in log-log plot is called light-tailed, 가벼운 꼬리 distribution. By the way, every straight line in the log-log plot called heavy-tailed distribution. So, as I just told you, the most important continuous random variable is Gaussian, which is light-tailed. Second most important continuous random variable is Cauchy distribution, and that is a representative heavy-tailed distribution. Now, here goes tantalizing question. So given this PDF, what is the mean value of this random variable x? And you all know what is the mean value of random variable. You have the sense, you have intuition. So usually you want to find the symmetry of this PDF along 0 in this case. So you are very tempted to say that the mean value is 0 because it's symmetric. Surprising thing is that Cauchy distribution does not have its mean value. Why? And we are going back to that problem. Got it? So Cauchy distribution does not have a mean. And since mean is not defined, its variance is also not defined. And we will see when we define what is the mean and what is the variance of a random variable. By the way, this light-tailed or heavy-tailed thing is not just for Gaussian and Cauchy. Actually, this is one of the reasons why we love wireless communication. Suppose that your internet connection to your machine is through Ethernet, or your internet connection is through Wi-Fi. Which one would give you better quality? Actually, in general, your Ethernet connection provides you faster, much faster connection. Why? That is this reason. If you transmit radio wave through, we don't have Wi-Fi access point, but anyway, what happens is that it emits energy, or if you want power, to almost every direction. Of course, modern systems want to beamform our energy, so energy efficiency or power efficiency is much improved. But anyway, it spread out the energy. And your PC or cell phone has very small antenna. And that small antenna only captures very, very small part of that emitted energy or power from the transmit antenna. So immediately after transmission and reception in wireless communication, you lose 10 dB, 20 dB, 30 dB, 40 dB. What does that mean? 40 dB loss means that your received power is 1/10,000th, 만분의 1 of the transmitted power. So its decay is very fast, immediately. Then you may say that, hey, wireless communication is doomed, right? But interesting thing is this one. In your electromagnetics, let's consider free space. What is the transmitted power? What is the received power from the source when you receive using the same antenna at 1 meters away or 10 meters away? If it is a free space. 10 squared, 1/10 squared, right? You may say, that, hey, 100th. Oh my God. However, consider in log plot. It just follows the straight line, right? Because it's 1/r squared. It follows power law. Sometimes we have scatterers or worlds where still the received power well modeled as a power law. In that case, it may have order 3. The problem of cable is this one. Suppose your cable that gives you very high quality in short distance has some fraction of power lost per 1 meters. Then what will happen if you have 10 meters? That ratio, common ratio, is raised to the power of 10. What about 1 kilometers? What about 10 kilometers? Your loss follows exponential distribution. That is light-tailed, even though it's not that light-tailed as Gaussian. So your exponentially decaying cable loss looks that way. So what we have is this one. Suppose this is distance in logarithmic scale. This is the received power in logarithmic scale. This is 1. Then you start from here for wireless. You start from here for wired. So there is some point of distance. After that point, wireless communication is much better. Of course, this is a very, very simplified argument. In reality, we put so-called repeaters. So we do not just connect the cables up to very far distance. Also, even though we have this exponentially decaying gain in the cable, if we use optical fiber, the loss is very small. That's why we have submarine cables that connects the world through internet. These days, Elon Musk says that, hey, we are doing wireless internet connection. But most of the internet traffic is still wired traffic, except at the end node. The last mile, so-called last mile, is heavily replaced by Wi-Fi. So we have wireless communication, but very, very short distance. So it's okay. Anyway, that is another thing related to log plot and power law. And another thing is financial signal processing. Probably you remember 2008 Lehman Brothers bankruptcy. At that time, what happened? People said black swan appeared. Actually, so-called black swan event is related to the power law. So suppose you are a seismology 지진학 researcher, and you have counted, researching the history that Mount Baekdu had eruption for every some minutes, and this is the recorded strength. Well, what you usually do is that this is the time in logarithmic scale, and this is the magnitude of the earthquake or eruption. And they put dots here. And what happens? Suppose you've seen some distribution like this. So even though very rare, right? 100 years, 1 year, big until small, it seems that your log-log plot shows some trend linear. In that case, the seismology researchers claim what? Hey, we may have very, very, very large earthquake or volcanic eruption in Mount Baekdu, and it may come soon. Probably he or she is assuming, right, a deterministic arrival. If it's still exponential distribution into arrival, is that what? Probably no. But this trend shown in log-log plot sometimes gives you an idea about never seen event. So, for example, if you plot this type of thing in stock market, you may highly predict one may let you bankrupt in some cases. You have, for example, trained your machine learning system, AI system, to assist your trade in stock market. The problem of current model is that it's like Bayesian inference machine. And the prior distribution is provided by your training data. And training data has no outliers yet, no black swan event yet. So your AI trader may assume that that kind of rare event, black swan event, may not occur. And it just provides you some statistical risk management scheme. And most of the times you are happy. Hey, I've developed an AI assistant that helps my stock market trading. I got a 20% compound rate. Hey, I will beat the legends like Berkshire Hathaway's, you know what I mean, right? And that kind of people. And suddenly the day comes. And that kind of thing happens, and you have no statistics or prior event like that, and your AI trader, trading assistant, just will say that, hey, I have a new data for my training. Bye-bye. And you get bankrupt. So be careful. Okay? Plotting previous dots, just drawing, in this case, two-dimensional scatter plot, is very, very informative. So never forget about this one. Anyway, the next one is Rayleigh distribution. And it has some form like this. Usually we set A equals 0. And in that case, it is related to the received signal power strength when we have non-line of sight in communications. That's not that important. Rayleigh distribution is heavily used or was heavily used in wireless communication channel modeling that has line of sight path. The last one is the Maxwell-Boltzmann distribution. And when I was at your age taking this course using Peebles' textbook of earlier edition, there was this Maxwell-Boltzmann distribution, and those names looked far from my interest. I had more interest in signal processing and communications. And Maxwell, well, I really hated to memorize those 4 equations. And Boltzmann, oh, I really hated the introduction to mechanical engineering and other physics-related thermodynamics. And actually, these Rayleigh, Rayleigh, and Maxwell-Boltzmann are all turns out to be related to Gaussian distribution. And Gaussian distribution is very familiar to me now, at least. And we will see what it is. But let me just say this. Maxwell-Boltzmann distribution is related to the temperature and pressure of ideal gas. 이상기체, as you learned in chemistry course in high school. 화학 시간 이상기체 방정식 기억나시죠? So suppose you have ideal gas with pressure P and temperature T. What does that mean? Every molecule in that lump of gas has same temperature? Actually, it turns out that temperature is related to the average, ensemble average of the kinetic energy of individual molecules. And this one can be understood this way. Probably mean is around here. This mean value is related to the temperature. And this distribution is related to the actually squared version is related to the kinetic energy of each molecule, something like that. This actually explains why our water, not boiling, still evaporates. Why? Even though it's just around 28 degrees Celsius, as you see here, some molecules have very, very high kinetic energy to set free from other water molecules. If we may define individual temperature of each water molecule, some water molecule in this cup has higher degree than 100 degrees. So it evaporates. Got it? That's kind of interesting interpretation of this Maxwell-Boltzmann distribution. Anyway, there is another Gaussian-related distribution called chi-square, and probably you heard about it in your statistics course. And we are going back later. The last topic is this one, and I have around 25 minutes. Need to be very, very fast. So let's take a look at the title. Conditional distribution. Here, distribution means if you want PDF, CDF, or probability mass function of random variable X. Now we have condition given an event in terms of that random variable. So what we are going to see is something like this. You've seen already that the conditional density of exponential distribution given t is greater than 5. Got it? So what is this one? This is the event, actually, that t is greater than 5. So given this condition, you want to find the PDF of the exponential distribution. So we've already been exposed to this problem. To make everything mathematically correct, let's define this calligraphic letter B as an event in terms of random variable, and this normal uppercase B as a Borel set, for example, interval 0, 1. Got it? So you see the difference? This calligraphic letter B means an event. So this event will be written as calligraphic B or sometimes A. Got it? And our event B is defined as X in the Borel set B. Got it? Now, we want to find something like density function of X given the event B, or CDF of X given X is in the Borel set B. Got it? And how can we define or derive these quantities given a distribution of a random variable X? So the problem is like this. You are already given a distribution of your random variable. It could be provided as in the form of CDF or probability mass function or PDF. In any case, actually, most fundamental distribution is what? CDF. Most intuitive distribution is PDF. Got it? Because PDF is what? A kind of limit of the normalized histogram. Got it? Anyway, so given the distribution of X, what is CDF of X given X is in the Borel set B? B could be interval, B could be some discrete set, anything. So this is the question. And interestingly, many textbook, undergraduate textbook, defines this one. But as I told you in the beginning of this course, every result stems from the axioms of probability measure. So actually, what we are going to do is not define this one. We are going to derive this result. Got it? So let's do that. Let me go back to that one. First, in order to warm up, let's consider this very simple event. As you see that, actually, we consider the Borel set in this form for CDF, actually. Now, given this event, right, what is the CDF conditioned on that? CDF of X conditioned on B is what? Interesting thing is this one. CDF is defined as the probability of event that capital X is less than or equal to this argument X. Now, we have condition. You may put B, calligraphy letter B, or you may write X in the Borel set B, right? So it's nothing but the probability of this event given that event. And we know how to compute already. What is the definition? We defined this conditional probability in that way. Right? This is the definition of conditional probability. Now, how can we simplify this one? When we have this semi-half interval, what is this one? X in B. And this is nothing but the CDF of X evaluated at B. What about this one? X less than or equal to B. So whether X is greater than B or less than or equal to B, you can simplify this event. And interestingly, you have this result. It's not difficult if you have head and not tail. If you have brain, oh, what is that? Okay, suddenly our president appears here talking about 분당 아파트. Anyway, so you have this result. Okay, I can derive. What about PDF? Conditional PDF. You differentiate and you have this result and you can write it that way. Okay. What about discrete case? Or what about now you have interval? That's not that difficult. You can show that CDF can be written that way and PDF can be obtained by differentiating the conditional CDF. Most interesting thing is this case. Actually, we've seen something similar already. What was the problem? Suppose X is Gaussian, standard Gaussian, and now you want to find out the density conditioned on the event that X squared equals 1, right? And I claimed this must be the summation of half delta X located at -1 and half delta located at +1. Why? Why, by the way? Why? So let's see what I have drawn. I really these days love playing with Gemini, AI assistant. And this figure actually is generated by Gemini. I provide proper prompt and Gemini generated so-called TIC-Z plot for my LaTeX handout. Amazing, right? And this is in Korea called 졸라맨, right? You already know that. But in English, it's called homunculus. Homunculus. Probably this homun means human-like, but anyway. So this conditional distribution, now well described in this figure. Probably you remember what is a random variable. We assumed that here is underlying random experiment modeled by a probability space, S, E, the sigma algebra, and probability measure P. And it generates outcome S. And what is a random variable? Random variable is a mapping rule that accepts S and generates a real number. So you may assume that there is 졸라맨 here. It reads what is S and finds some real number labeled by S. So suppose S equals 5. And this 졸라맨 finds a real number that is associated with S equals 5 and gives it as an outcome, right? Output. That is random variable. Now, what is conditional random variable, if we want to call? There is another 졸라맨 here, and it inspects whether generated X of S is in the Borel set B or not. If it is in the Borel set, what happened? Okay. Something's seriously wrong, okay? And it accepts the outcome and generates it. If X of S is not in Borel set B, then it asks to generate S again. Got it? Now, let's apply this idea to this problem. Gaussian with X squared equals 1. Of course, X squared equals 1 is too restrictive, so X squared is approximately 1. Then what happens? Probably this guy will check whether X is either 1 plus minus epsilon or negative 1 plus minus epsilon. Now, this is Gaussian, and there is inspector who checks whether it's near 1 or negative 1. Now, the output would be near 1 or negative 1. That's why I claimed this, where it is. Yeah. Gaussian distribution given X squared equals 1 is just 2 delta functions. Same thing. Got it? So never forget that figure because that's very important. When you generate conditional distribution from a distribution, random number generator, actually that is the structure you are going to use in your programming. So it generates either you accept or reject and resample. That is the simplest way to just use single random number generator. Anyway, so this case can be well approximated and gives you very interesting result. And all these things combined together appears here. So in the previous examples, we assumed the Borel set we choose is either half interval or interval. Now we consider general Borel set B. Now the result is very interesting. You can show that. Let me show you the PDF first because it's intuitive. And it's related to that 2 졸라맨 figure. See that? You want to find the density of X conditioned on this X is in the Borel set B. Now, still you are interested in this density, even though it should be modified. So you have f of X appearing in the right side, right? See that as I repeatedly told you, whenever you have conditional something, actually you are going to modify unconditional something. See that? You want to find the conditional PDF of X. Here you have unconditional PDF of X. Now you are inspector Jollaman does what? Does put here indicator function. See that? If X is not in the Borel set B, its density is 0. What does that mean? It never appears in your normalized histogram. Does it make sense? Right? So suddenly this formula really intuitive and makes sense. Right? And see other things. What about PMF version? You want to find probability mass function of X conditioned on some event in terms of X. Still, you have the same thing appears here. You have probability mass function of X, unconditional mass function of X, that is inspected by the Jollaman, right? So you have indicator function. That's why I emphasized indicator function from the beginning. Most of the courses, especially for engineering, probability random processes, they rarely use that indicator function, but I really love it. Probably if you are retaking this course, you immediately know the difference, right? And what about these denominators? Actually, these denominators appears here, two reasons. One, if you derive the result, that appears. Second is that you want this one to be a legitimate probability mass function, which means that if you sum up for every X, then sum must be 1. Now, if you sum up for every X, what happens? This is what? This is constant. If you sum up, actually, what is the sum of this one for all X? It appears in the denominator already, right? So it's 1. Hey, too simple, right? So your intuition really works. Your conditional mass function must be unconditional mass function inspected version. Now, this product may not give you legitimate or lawful PMF. Now, let's just summation, sum over all X. Then you must have some of this one appearing in the denominator. That's it, right? Now, let's see the PDF. I know. Some of you may say that, hey, why Professor Cho does not give us derivation? As I told you, this course will no longer be third grade course. It gives you, I really want to give you an intuition and what's the behind the formulas. Got it? That's why this course is really different from my previous courses too. And now let's see this one again. So this is conditional density. You know that it must be unconditional density inspected, right? Now, integration of the right-hand side must be 1. That's why you have this numerator integrated over all X appearing in the denominator. Got it? Anyway, that's my message. So we are done with the conditional distribution. Now, here goes something far beyond usual undergraduate courses, but I've decided to talk about it. Suppose you want to have a chain rule, because you remember from chapter 1, what was the foremost theme repeatedly appearing in this course? As I told you, conditional something. Second, conditional something related chain rule, and total probability theorem, and Bayes theorem, and independence. So we've just seen conditional CDF over PDF or PMF. Now, what about related chain rule? And here goes strange thing. See that? This is a joint probability of X in the Borel set B, and X equals the point event. So this is a point event. Point mass. And if this exists, then what? This is event A intersected event B. And we must have what? P of A times P of B given A, or P of B times P of A given B. Actually, this is exactly what we expected. So far, it's okay. the problem occurs here. What about if X is continuous random variable? In that case, where here you see the asymmetry, non-symmetry. See that this looks like PB given PA given B, PA given PB given A. However, there is nothing here that corresponds to the leftmost side. Why? Because there is no expression here. Actually, we may have something uncomfortableness, but actually that can be resolved by using, again, radon-Nikodym derivative, which is not taught even in some graduate courses. But you know that this must be true. Anyway, so we have chain rules. What is the next? Total probability theorem. So let's see. Suppose you introduce a partition of the sample space S using events A sub i's. In that case, what is this one? Probability of capital X less than or equal to X. So if you replace this as a probability, this is nothing but our previous total probability theorem, right? And if you differentiate, then you get the next total probability theorem. And again, the same form appears again and again. CDF of X is what? CDF of X conditioned on the events times probability. So as you will see later, the right-hand side is simply the average conditional CDF. That is unconditional CDF. What is this one? The right-hand side is average conditional PDF. That is same as unconditional PDF. That's the interpretation of these two results for total probability theorem. What about Bayes theorem? Bayes theorem, as you know, that it's a simple combination of the definition of conditional probability and total probability theorem. So we've seen these two already. So we naturally have the result, but we've seen it already. See that? Conditional density of X given the event is unconditional density gated by the inspector and normalized by the entire integration, right? Same for the PMF. Now we substitute this one and get interesting results like this. By the way, what is the purpose? What is the usefulness of Bayes theorem? You can use the results for statistical inference. You want to update your prior knowledge using new observations provided by events. So see that? You want to update your prior knowledge by multiplying some correction factor to find conditional distribution, conditional probability. Same thing here. Ready? So combining the definition of conditional probability and total probability theorem, you have different versions of Bayes theorem. Ready? Oh, by the way, I've not only put this form, but also the intermediate forms. And you will immediately see why we have these denominators. As I told you, what? The summation of these events, right? For all I, because as I told you, I is what? A sub I is a partition, right? So whatever condition you have, if you sum up for all events in the partition of the sample space, you must have always probability 1, right? So the left-hand side summed over for all I must be 1, which means that this numerator summed over for all I must be divided by itself to become 1. That's why you have this denominator. Same thing again here and there. Got it? Why do I emphasize this one? Because I myself had painful experience. When I was even, because this topic is usually covered in graduate level, I tried to memorize this one without knowing the kind of mechanism governing this one. I derived and tried to memorize. It was a stupid idea because it's obvious to have this denominator. If you have that numerator, never forget that probabilities summed over for all, then you always have one, the unity. Got it? Anyway, so these are just the special cases. Now, finally, we are going to talk about independence. The problem is that we only have one random variable. What independence? But we remember that when we learned independence, what was the following words? Independence of between two events, right? So we must extend that idea. As I told you, every result naturally comes from chapter 1. We don't need significantly different new idea. We just reuse chapter 1 idea again and again and again. So even though the problem is that we have independence of random variable and event, independence between a random variable event, we must transform this to somehow independence of an event with another event. How? We already know that. We form an event in terms of random variable x. So something like this. So what we are going to do is that we choose some Borel set B and consider this event. Sorry about that. We already have B, so probably A. Okay, let me use A. And we have already an event B. The problem is that how many choices, given this Borel set and event B, how many different events can we make with a random variable x? Uncountably infinite, because there are uncountably infinite number of Borel sets in the Borel sigma field. Then what do? Don't scream, right? We remember that every Borel set can be generated by countable set operations on this type of, let me have one more minute. So we instead choose this type of Borel set. What it is? It's a CDF type thing. Got it? Anyway, so we may choose any real number here. So we consider every event defined in that way. If we can show that this event is independent of that event, we will say that random variable x is independent of this event. Got it? So every event in terms of the given random variable x is if independent of the event b, then we will say that random variable x is independent of the event b. Got it? That is the idea. And everything comes very naturally. And here we are. We finished chapter 2. And you may say that, something not enough. You will see it again in the later chapters. So here goes the quick summary. We've studied what is a random variable. Now you have the answer. It's a function from sample space to the real set. What is the induced probability space? That gives us what? To put every random experiment generating real number together here with the same sample space, same sigma algebra, only different induced probability measures. And good thing is that this is same as the CDF. And CDF is very important, and it defines PDF, even though we have our intuition from the limit of the normalized histogram. And we've seen parametric families, discrete, continuous, and eventually 4 repeating themes: conditional probability distribution, total probability theorem, Bayes theorem, and independence. That will be repeated again and again and again. Okay, that's all for the day. And you will take your first quiz on Wednesday immediately from 2 p.m. Okay, that's all for the day.